Hello and welcome everybody to Advent of Code 2022, day 21. And I'm still behind, still 2 days behind. Almost caught up yesterday to get back to be doing the day that we were on, but this problem, I went down a wrong track with it and I kind of tied myself up in knots when I should have actually just done a simple approach. That is what I ended up doing to solve the problem. But I had axed that approach previously because, again, I had managed to confuse myself and it wasn't working for me. So I went down a more complicated approach, which also didn't work. So then I went back to the original approach and got it working. And yeah, anyway, bit of an odyssey, but we got there. So, day 2021, or day 21, monkey math. The monkeys are back. Delighted. I love those little guys. This time, they basically, there's sort of like a number pattern thing going on here. So the monkeys are shouting stuff at each other. So each monkey has something that it has to shout. It's like a number in this case. But it also, each monkey could shout a combination of other monkeys' numbers. And so you end up with this big sort of nested equation type thing that you have to solve. This is the example they give you. So they give you each monkey and then what the output of each of those monkeys call is. So if you were to go with this guy, all he does is he just shouts the number 5. But the root monkey here, he shouts whatever PPPW is or SJMN is, the sum of those two numbers. So you have to basically evaluate each of these going down in a tree to get your answer. And that's pretty much it. They ask you to figure out what the output for the root is. So let's have a look. Not very much code, quite short. Ruby's eval method comes in to great effect here. So basically what I do is I read in every line from the input. I split it up and I create a hash of all the monkey commands. So each monkey, denoted by a string here, gets a lambda expression as its value. If the monkey is just saying a number, the lambda expression is basically just the number itself is all that gets returned out of the lambda. If the monkey is calling out to other monkeys, then the lambda that gets returned is an eval of basically this string in here. And all this string does is it says, okay, go to my monkey hash, find whatever that symbol is, which I have split up here, whatever the operation is, and whatever the other monkey is, and do the calls on their respective cells inside the monkey hash. And that's it. At the very end, you just call the root monkey and the call method, which evaluates that lambda, and then this will essentially just do like a recursion, and it will just go down the whole way, down the whole chain, and then it'll return you the value at the end. That's it. Simple as that. This took me very short amount of time to write, and it works pretty nicely, and it's pretty quick as well. So we have a look at part 1. There you go. Finishes in 0.02 seconds. You have to imagine as well, or appreciate as well, that for the input of this, there's 5,000 unique nodes in it. So yeah, it's quite a bit. And that is it for part 1. Nice and handy. So then for part 2, they mix up the problem a bit, and basically what they tell you is that there's a node, HUMN, human, and that's actually you. So what you're trying to do now is, instead of just evaluate what the root node value is, we're told that the root node value is now an equality expression. So we want to know what... Thanks, Kat. We want to basically figure out how to make that equality expression equal, so that for the root node, the left equals the right. And you can do that by modifying the value that you say. So you're basically trying to modify human to get the answer at the root to be equal. So there's a couple of ways you can approach this. The first way I thought to do it was, well, I can already compute each side of it. I reasoned that only one side is going to be affected by the value of human. So what you do is you compute both sides, figure out which one gets modified by modifying human. And then all you're trying to do is you're trying to find the value, that makes either the left or the right side end up being equal to whatever the constant value is, the one that's not affected by human. So you can do that, but the numbers are really big. So it ends up being some like 13-digit long number. So I was trying to do like a simple binary search on it, and I just couldn't get it to work. I kept going positives and negatives, and I kept overflowing myself. So I was like, nah, this isn't a good way to do it. There must be a better way. So then I started trying to reverse the tree with some different maths to try and figure out, so basically trying to flip the operations around to try and work out what it was. That didn't work for me either, because I ended up in these, like, I ended up finding loops inside. As I reversed the operations, I ended up finding loops inside the tree. So I got it to work for the sample, but then I couldn't get it to work for my input because reasons. There was basically, it was ending up in infinite loops, and I was getting these stack overflow errors. So I was like, okay, this isn't going to work either. So I went back to my binary search, and I just wrote the binary search properly, and it worked. So we'll have a look at the code for that. Quite simple. We build our tree, our monkeys in our monkey tree of operations in the same way, except this time I want to skip the human node because we're going to manually set that value every time we call this over and over again. I have an infinite loop here, which I'll break out of when I've found that I'm at my exit point. So basically my root node has it's the sum of this value and some other value, which ends up computing to this. So I know this value never changes regardless of what the value of human is. So what I'm trying to do is I'm trying to figure out where this value ends up equaling that value. So my diff becomes 0 then, and then I can print out that number and break. I initialize with this, this massive number here, and I found this by trial and error, just literally calling different numbers in the console until I found something that got me sort of close. It's got the number started to reduce, the difference started to reduce in the right direction. So that's my seed number. And then the only thing in here that's kind of clever, I take the diff, and if the diff is greater than 1,000, then I basically use that as my modifier for my binary search. So I increase and decrease by a factor of the diff divided by 1,000. So it compresses that search space down quite a lot. Then eventually I get down to, some number less than 1,000, and then I just swap to using 1, and then it rattles itself down and gets to the very end. And that's it. Binary search gives you the right answer. And it's not incredibly fast, but it's also not incredibly slow. It works, I think it runs in about 6 or 7 seconds or so. Let's see. What's it going to give me? Oh, no. Oh, there we go. 7.7 seconds. So not crazy fast, but it does get you there. And it was it was the simplest way to solve this. I didn't only had to write the binary search logic. The rest of it is basically all the same. And if I had written the binary search logic right the first time I did it, I would have had this solved yesterday. But I didn't, and I got myself a bit confused. And then I wasn't really interested in working on it yesterday evening, so I just left it until this morning. But yeah, that's it. That's day 21 done. Maybe I'll get a look at day 22 later on today. Maybe I'll try to get caught up again, because we're on day 23 now. But we'll see what happens. But yeah, that's it for this one, guys. I will see you soon. Bye bye.